learning-based approaches of uh, classification. So this learning-based approaches of classification we will be discussing. With these points, we will be just speaking about the background. Then we will talk about the learning systems. Then we will be speaking about the perceptron. Then we will go to the artificial neural network, basic considerations, how it works in some detail, and then references. So the word classification starts from the classifier. So we need a classifier to deal with the real world phenomenon, so that we can have some statistical decision making capability. So a classifier will roughly subdivide the sample space uh, into decision space, and each of these decision spaces will be linked with a class. So vectors of different classes will provide significant challenges in making them distinguishable. Therefore, we need a classifier to make the distinction of the classes feasible or possible. Then we quite frequently find that though a classifier will be doing the classification, there shall be also uh, misclassification, and this misclassification is due to the uncertainty linked with the decision making process, and this is not linked with the deficiency in the decision regions. So the most simple way, as we all are familiar now, that the most simple way shall be to have a linear discriminant function, and this comes repeatedly because of the fact that this linear discriminant function shall be the basis of all logic that goes into the formation of a classifier. So how we define a straight line, that particular consideration leads to the definition of a classifier. So here we will have a function g of x, that is a combination of the weight matrix w of t multiplied by x plus w naught, that is there is a bias or a threshold weight. Now the combination of the linear discriminant functions basic philosophy linked with the classification process can be also linked with the learning mechanism. Now learning mechanism is linked with a classification process that will classify patterns by following some decision logic defined beforehand. So in the learning process, there shall be class boundaries that will be defining, that shall be defined by the use of certain thresholds. Then we shall find later on that the learning mechanism is key in removing the randomness seen in the classification process, and learning mechanism to start with is linked with simplistic processes, but can be also configured for all known situations that we see in the real life situation. Now, this whole learning process can be depicted by this particular diagram. We here first we will define a say model, a mathematical tool, a logical tool, mathematical tool, computational tool that will be fed with training data. Now that particular training data will help this model to tune or to learn, and then start to do predictions. So once the predictions are made, there will be a feedback part, and then the predictions will be checked. If the predictions are right or not, that will be validated. And we in this validation process, if we find that the predictions are not that relevant, that can be also checked in the domains where we want to use it. So where we use it, and if we find that the trained model is not sufficiently capable to deal with the real world situations, we can check its performance with the test data. So with the test data, if it is capable of dealing with the test data, from the test data, we can generate some feature also. That particular feature can be used to make the training better. So that part of the feature generation now will pass through the validation stage, and this shall form a part of the uh, uh, that shall form a part of the training data, and that part shall again go to the training of the model. So this part shall go on continuously, shall go in some cycle, will have a feedback loop, will have a training part, will have a testing part, will have a validation part, will have a feature generation part. So this will continue in a cyclic manner. So this is quite uh, a generic characteristic of the learning systems. Now, now the base of the learning system is formed by the artificial neuron, as proposed by McClock and Pitts. We have talked about it previously, but for a sake of building the continuity, we are repeating it. So here there shall be a number of patterns fed, capital X1, capital X2 dot dot, capital Xn multiplied by the weights W1, W2, Wn, and then this will be a this small capital X naught shall be a bias. Similarly, there can be a weight bias W naught. Now these will be all summed up here. Then there shall be a summation block. Now this summation block will create this particular representation, Wi multiplied by xi summation from 0 to n, that will go through this threshold function, or a switching block, and then generate the response. Now this all comes from the biological linkage, as we are familiar with. I have talked about in the previous slides, with the dendrites connecting with the dendrites connected to all the nearby neurons. We find that a neural network shall be formed. Soma will be the cell body where the summation and the thresholding takes place. So like this, the McClock-Pitts model was developed. So the McClock-Pitts model can use a number of switching functions, or transfer functions, that's small f, hard limiter, symmetrical, hard limiter, log sigmoidal function, tanh sigmoidal function, linear function, and so on and so forth. Now the key point to note there shall be the fact that this particular neuron model in 1958. So from 1943 till 1958, this particular McClock-Pitts neuron model served the basis of generating learning capability in the classifiers. But in 1958, due to Rosenfeld, a new theorem came, that is called the perceptron learning rule, for which the perceptron was developed. Because for this particular rule, we saw that the neuron could tune, neuron could learn, neuron could trained, and there we found that that due to this perceptron rule, the thresholds could be tuned repeatedly depending upon the situation. Now the basic considerations of the perceptron learning rule can be summarized by this particular relationship. So from a normal perceptron, we will get the response to be y out. That is a combination of the weight function multiplied by the pattern vector x, where for the training we find that both the patterns and the responses or the desired responses are fed together. So the small x will be the pattern, small y will be the desired uh, responses. So the difference signal between this y out and the desired response can be represented like this: y out multiplied by yt that we want. So this can be also represented like this: wt w of t. So that is a time dependent function multiplied by the pattern vector x count of t minus the target y of t yt, this thing squared. So this will be the cost function. Then learning will take place where new values of this weight will be defined like this: w uh, taking the count of t with t plus 1 value, taking the w the count of I, the present value, then the rate of change of this e value compared to w of t multiplied by the c. Now this c will be the step function, how we scale uh, this rate of change of the difference between the present value and the desired value. Now this particular relationship is called the gradient descent function, or this is called the gradient descent, because this del e by del w, that is the gradient formed. So this particular gradient descent in each recursion will be or should be decreasing. Therefore, the descent term. Therefore, this is called the gradient descent uh, function, and that forms the key in sustaining the training that the perceptron cell has, and this forms the basis of the learning of the McLeod pit uh, neuron, and it converting to a perceptron. Now, so this whole thing can be further shown in one more slide like this, where we have two calculations. One will be a forward calculation. Then there will be a comparison with a reference response, and the difference shall be again fed back, and the weights will be continuously varied. So this process will go on continuously the till the responses are found to be closer to the desired value. So to do a classification, we need to fix the class codes beforehand, and this particular red dot will be targeting to come closer to the desired class code, and that will decide the classification performance of this particular system or this particular network. So we have seen beforehand that there are three modes or four modes of learning. The first mode is the supervised learning, and with the perceptron learning rule, the supervised learning mode was considered. Supervised learning mode was taken to be the basis of the perceptron learning rule. So there we need the training and the test sets, data sets. Then we further need to have a linkage, a prior knowledge between the pattern and the target. So a prior linkage between the patterns and the target should be well defined beforehand, since that will form the key of the training. So here we can see that how the training process is sustained. So we will feed here some some data patterns. Then here we have here the target responses. So the first two columns shall be the uh, pattern data, and the third column shall be the desired uh, responses from the system. So to start with, we will get these particular results. These particular results shall be continuously compared with this desired set of pattern responses. The difference will be calculated. That will be fed back to tune the weights that shall be there in the connectionist links between the neurons. So the whole thing will run like this. Suppose we are dealing with the sepal, with the sepal and the petal of the flowers. There are two particular classes, class 1 and class 2. So we need to here have the features: define length of the sepal, the breadth of the sepal, width of the sepal, length, width both the sepal and the petal. So they will form the feature set, and how they are linked to the classes. This part is defined beforehand. So this will form our a priori probability, or our a priori knowledge. So once we know that, we can now see how the perceptron training will take place. So we will see that first, to start with, we will have the pattern feeds coming. Then then it will be scaled up, thresholded. Then again, that is for the logical n, and next one shall be a case for the logical or. Then that's a case for the logical not. So for different cases, the the configuration and the combination of weights shall be varying like this. So a simple network to start with, that is the case. So how things will be varying. So the weights and target will be fed like this, and a bias is also fed here. That will be scaled by a weight. So this will go on, and that will have a threshold. So this particular threshold shall be compared, or shall be considered for doing the comparison for the responses, and networks classification will be based on this particular thresholds comparison. And so now for the logical end, there is one such depiction. So how that will be the case. So weights, we will first stick with the random weights, and if we use the perceptron learning rule, we can change the weights in the recursions that shall be made. But if we take it and do calculation step by step, then the values should be calculated manually, step by step, and then that will be known like this. So if we have these sort of values, the whole process can be shown to be like this. So in a calculation done step by step, that will look something like this. So for the feeds of -1, 0, 0, so if we take here weights 0.3, 0.5, 0.4, that shall be scaled like this, and then a value will be seen to be -0.3. So that will be compared with some threshold. So if the threshold condition is met, that will be said to be 0. Same for the second case with pattern feeds -1, 0, and 1. So that will be found to be giving a value of -0.7. That will be again considered to be 0. So this way, step by step, the process of the training of the perceptrons will be continued. So how we see? So there are a few considerations. One will be that epoch. So that will be the cycle, that will be the session that will be used for doing the training. And the second one is that error part, that is the difference, the difference between the response we are getting now and what we want. So these two things will come to us repeatedly. So we will have a target value. So the response that we have now should be compared continuously with the target. So the output O will be compared to the target value T continuously. For the inputs I with count of j, scale by weight wj with a learning rate represented by this LR. And this normally to start with is taken to be a small value, 0.1. That should be a fraction less than 1, and it is between less than 1 and 0. Now, with these sort of values, we can train a perceptron, and through that we can lay certain decision boundaries. So the decision boundaries can be sometimes found to be continuous linked planes. So those are called hyperplanes. So plane linked together. So that we need here certain discrimination, certain discriminant functions to lay continuously coexisting boundaries. So with these sort of classification tools, we can deal with uh, classes that are linearly separable. So while we have linearly separable classes, the perceptron was found to be quite reliable. So a case of where we can have a decision boundary and a linearly separable situation, a class linearly separable class situation with two broad classes and two broad planes, capital X1, capital X2, with a straight line boundary separating out the letters A and B. So that way the classification is done, or that way the segregation is done between the classes. Now, for a perceptron case, we can have a non-linearly separable class too. So for a non-linearly separable class, we can use the combination of weights and the threshold and the bias values, combination of weights and the bias values to formulate non-linearly separable classes. For the linearly separable classes, we have a straight line separating the two classes. But for a non-linearly separable classes, we might have two separate categories, or two separate sets of boundaries. So one set of boundaries shall be lying in this third quadrant. We can have one more a boundary lying in the fourth quadrant, then one more boundary lying in the first quadrant, and one more boundary lying in the third quadrant. While the classes in the first and the third quadrants are of the same type, are of the same class, and the classification in the second and the fourth are of the same type. So for these sort of situations, we have non-linearly separable classes. This can be generated by the use of a perceptron, and here we need the combinations of the weight and the bias values. Now let's go through some of the past developments. In 1943, McCulloch-Pitts model was developed. That was the basis of the neurocomputing. That was the beginning of the neurocomputing generation. Then 1958 came a big change when the perceptron learning rule was proposed. There we had a three-layer system, a input node and an output node, and one more layer that will be linking the IO nodes. That is the association layer. So that could learn patterns and could relate uh, the patterns with the desired classes. Then in 1964, two people, uh, two researchers, Minsky and Peppard, showed that with the single layer or this perceptron cannot learn the logical XOR case quite clearly. So since that was proven, so that one turned out to be a big detrimental factor in the research of neural network. So people thought that that is the end of the research in the field of the neural network. Then again, there was some more development reported in 1974 by Verbos when he proposed back propagation. So there he talked about the back propagation used with the input, output, and the hidden layers. So that marked to be a major change compared to what Minsky and Peppard had said, and that one had great backing with the theories linked with the perceptron learning rule. Then the biggest breakthrough came in 1986 when there was a person by the name Rommel Hart, and he was supported by Macmillan. Rommel Hart showed that if we could um, group all the perceptrons in layers, and then we can train it with the back propagation, then that particular neural network that he called to be multi-layered perceptron can solve multi-class classification problems. So that was a big breakthrough, and that saw a resurgence of the neural computing technology. That was a major breakthrough, and that saw a new growth, in a new surge in the funding towards the research of neural network uh, technology. Then steadily later on, or in several cases, concurrently there were developments in the Hopfield uh, Hopfield network. One layer of fully connected neurons. Then there is a self-organizing map SOM that was first proposed by Kohonen, that is based on the unsupervised learning. He's a living legend. Then one more big development took place by the name of the radial basis function. So that particular radial basis function, based on the use of the Gaussian function, could deal with a lot of real world situations, and was found to be quite successful, and have shown to demonstrate, or can demonstrate fast learning. Then in 2009, deep neural network was developed. Now let's go through one more time how the biological or natural neurons work and group. They will have a nucleus that will be inside the cell body, and they will be surrounded by the dendrite by the dendrites. Dendrites will formulate or will create a neural network by joining or by connecting the nearby neurons in the biological setup. So this same thing, when we consider, will roughly have signals propagating through the dendrite. So neurons will be propagating the content through the dendrites, or neurons shall be collecting the signals through the dendrite. Then they will send out spikes of the electrical activity through the axon, that will split the whole content into thousands of branches. At each of the branch, there will be a synapse, and the synapse will be converting the activity to certain responses, and the learning changes that will take place will be coded in form of certain neurochemical uh, changes, and that will be linked with the capability of the synapses to learn and generate the responses. So that's how the biological neuron system will work. Same thing is shown there in this diagram. So this will be how the brain shall be conveying the content from the brain part, cortex part, to the rest of the body through the use of the neural network spread all around the biological structure. So the patterns will come through the dendrites. The cell body shall be the processor. We will find that the synaptic content shall be the link, that will be the link to the neighbor, forming the network, and then the axon shall be the output that the system will be generating. So this is the basis of formation of the biological neural network. So here we have seen it before, and how that can be represented by the use of diagrams, and can be represented by the use of the mathematics, as was shown by McLaughlin. So here we have the responses, or the patterns coming through the dendrites. These boxes can be the weights. Here the summation will take place, and there will be the threshold generated. Now this thing will be done in the cell body, and then the response will be conveyed by the axon structure. Now here we see that there are few components. Building blocks of the neurons are, we will call them nodes or units. So we will have the input coming to us, pattern input. Then we will have the activation. Then we will have one response, output response, and going out. So this will be the main components of the neural network. So the similarity between the biological neuron and the artificial one, it can be seen here quite clearly. So here are the dendrites conveying the contents. Here are the signals picked up by the neurons from the sources, scaled by the weights, going through the summation block, say branch by branch, and then summed up there, and then there will be a switching or an activation function will be generating the response. So we find that this particular block is trying to replicate the biological one. So how it functions, we can see from this diagram. So so here we can have a feed coming from through the small axis, then scaled up, and then going through the summation, and then will reach the y. So y will be the response of the network. So we can have different weights. So since there can be different patterns fed to it. So all these are therefore scaled up by the weights W1, W2, Wm summed up. So summation block will look like this. Then the response Y will be a summation of or a thresholded value of the response to the summation that we have shown there. Summation of the patterns scaled by the weights. So this will be the response Y. So therefore, how they function in the true sense. So the pattern feeds come weighted or scaled. Those will be scaled up or scaled down. Summation coming here. Here will be a transfer function or an activation function. Will be finally giving us the response Y. So if we take it to a much bigger scale, we can have a number of weights, a number of here patterns shown. So all those patterns scaled up with different weights, going to different summation blocks, and then going through different activation functions. They will generate YKs, different YKs, and then they will lead to the summation, and then they will go through one more activation function and finally generate Y. So this sort of a structure, though it will be based on the perceptron, but many of the perceptrons group together to deal with a much complex classification problem where there are several characteristic features that should be given priority feature wise to have better classification, can have this sort of a network configuration. So how it weights, how it functions, how it works. So we will have the weights fixed randomly if we want to deal with the digital XOR table. So we need to set the logic step by step. Then we read the patterns from 00, since 00 will come first. Then we will need to compute the responses that the network will have from these zero zeros. Then we will be comparing that to what we want. So if this is reached in the first cycle, then it's fine. And if it is not reaching this desired value, then we will change the weight. This will go on in a loop till the condition is met. So this will require some number of iterations, and we can have a threshold fixed. Then if we group the neurons in layers, as was proposed by Rommel Hart, that will look something like this: multiple layers, so multiple activation functions. So there in the front end, we will have the patterns coming in, scaled by weights. Then in the first layer, they will be generating some threshold values or some values like V's, and those V's will be going through the first set of the activation functions. These will be generating the Y's. These Y's will be further scaled up by weights. They will go through one more layer of activation function, will be generating a further set of Y2 this will go through the next set of the activation function, and finally give us y2, that will be the final response, which will be compared to the desired values. And if they are not close to the desired value, a comparison shall be done, and the difference part will be fed back, and all the weights layer by layer will be tuned, changed, till this y2 is close to the O1s. So we can have here two broad look or broad processes of computation. The first part is the forward propagation. There we have the bias nodes. Bias nodes are required to reinforce one particular decision. There in the so we can add one node to each layer that has a constant output. So in the forward propagation, we will calculate from one layer to the next one, and for each of the neuron we will calculate the weighted mean of the input, and then we will calculate the activation function. There can be firing rules. There are threshold rules. There are the perceptron rules. So that will depend on how we configure the structure, the network, to deal with a particular situation. So the firing rules are something like this. One will be the sigmoid function. There can be two types of sigmoid functions. One is called the hyperbolic tangent function, defined like this: sigma of this v, giving us 1 minus e raised to minus v by 1 plus e raised to minus v. So then there can be one more sigmoidal function that is called the logistic sigmoidal activation function, where we have the sigma v as 1 by 1 plus e raised to the power minus v. So this is hence the most common feed forward structure of the multi-layered perceptron, or the feed forward ANN. So the feed forward artificial neural network. So the most commonly used throughout the throughout the 90s and most of the 2000s. So so in the multi-layered perceptron, we find there will be an input layer, there will be a hidden layer, and there will be an output layer. So these will work together, and these green, blue, and brown circles are nothing but the MATLAB pitch defined and later on changed by the perceptron learning rule called the perceptron blocks. These are the perceptron blocks, and the perceptron blocks can have linear transfer function. They can have log sigmoid transfer function. They can have 10 sigmoid transfer function. So depending upon the situation, depending upon the requirement, we can use linear transfer function. We can use log sigmoid transfer function. We can use 10 sigmoid transfer function. So the whole calculation process shall be for a vector x. We need to scale up with w's. So if we have a number of patterns with the vector, the count going with the I, so xi multiplied by the weight matrix wji plus a threshold summed up together will form vj of n. So this will go on, and this will be fed to the activation function that will that will result in y count of jn. So this will be the response of a particular neural network layer. So if there are a number of activation functions, so this y will be counted by this count of j. J can be from 1 to n. So this is one more type of neural network called Adaline. So how it works, we are just showing it through the slides. So for 0, 1, and 2s with varying weights, it will go step by step like this. So how the calculations go on with the weights, these slides are showing that part. So how the bias is used. So here is a bias value. That particular bias value can go up to this particular neuron, can go to this particular neuron, and to this particular neuron. And the significance of the bias lay in the fact that if we want to give priority to a particular discrimination, a particular boundary to be laid, we can use a bias function, or we should use a bias value. So for the case of 0, 0, how it goes here, there is the step, there is the computation. So at node 2, that is the node 2, so this will be the value generated. So this way the whole process will go on step by step. At node 3, that is the value shown. Node 4 will finally have a activation function that will be shown to be like this. From the previous slides, these two values will come, 5.9 there, 5.2 here, and 2.7 will be the bias going. So that will lead to this particular value. So for 0 and 1, there shall be a change. Similarly, at node 2, so this particular value will come. Same way for node 3, one more value will come. That particular value will go for the calculation of the value at node 4. So this will be the result. So once we have these values coming for all the nodes, we can have a density plot. Density plot will say that around a boundary, how the responses coming from the network are grouped. So if they are grouped in linearly separable, well-defined regions, we can say that they are doing the classification task properly. So a density plot can be generated, and that will tell us how the classification process has gone through, or how the classification performance is. So this can further show us, if we plot all the values of the weights that were used in the computation week, and then plot it in a 3D representation, we can see that the weights will show us huge variation. Weights will change, weights will rise, weights will fall, weights will grow, weights will shrink. So the weight, that particular weight change can be seen to be like this, something like this. We can find out that the network learns non-linearly separated set of outputs. We need to map the output, that is the real value, into the binary values. So this will take place in the forward propagation part. So the training will be the most crucial part, during which the learning will take place. So here the weights will be determined by the training process, and in the back propagation mechanism. So once we give the patterns, we will be generating a set of responses. We shall be comparing the responses to the desired responses. The difference will be used for changing the weights. So once we do a calculation in the forward pass, next we do a backward computation. So these will help us to readjust and tune the weights that we took while we started off. So the weights will be continuously changed and will be finally determined by the training. And at that, once we have seen the training has come to an end, then we will have the final set of the weights generated by the system. And in each of the training epoch, we will submit a training set of values as the pattern feed. We will calculate the differences. We will be then readjusting the weights continuously so that we make the present values come closer to the desired values. Finally, a cost function of the system is generated like this. The mean square sense of the difference is calculated uh, like this: y of k minus t of k, tk, yk minus tk. So tk will be target, yk is the generated value. So summed up, uh, squared, and the k count will be going from 1 to k. The whole thing is half. Since mean square sense we need that, this particular definition will act as the cost function and will determine or will quantify the level of learning that has taken place in one particular neural network structure. So this, while we see for the complete network, we find that the weights will be changing layer by layer. So a change of weights will take place there. Then in the middle part, a change of weights will take part in the first part, in the first layer, in the front end portion of the network. And there will be further changes in the values in the last end of the network. So this will continue while feeds come from the transfer functions, small f1, small f2, small f3, and they will be scaled up. Values will be scaled up by the weights and will be further switched or will be going through the transfer functions f4 and f5, and finally will reach and the f6, where once it goes to the activation, the y will be generated, and this y will become compared to the desired one. So this, as we have referred to previously, is the gradient descent um, mm, weight tuning. So this new weight wjk will be generated at t+1, means the future version of the weight will be dependent on the present version plus the minus sign that the gradient, since it's a gradient descent, so the learning rate will have a negative scaling, and that particular value shall be between 1 and 0, a fraction between 1 and 0, and that will be the gradient will be defined by the partial differentiation of the difference function e of x by the weight, that is del of wk. Same way, a similar function for the future version of the bias value can be also calculated or can be also shown. That will be theta k. So these two shall be crucial in dictating the training of the a and n. So if we use a sigmoidal function, we can have a differentiation of the difference function giving us a value of that type, which can be shown to be del of j, del j coming from the differentiation of the function small f dash, that is the differentiation of the function f taking the value net j. So net j will be the summation of all the weights, scaling the patterns, and then thresholded, and then a difference between the target and the present value, and the logistic function will have a derivative of this type. Sigma dash of t is equal to sigma of t multiplied by 1 minus theta of sigma of t. So if we consider one more time, one more logical or a digital uh, logic function, then we will find that if we start with some random weights and do the forward computation at the bias, we see a flow of the computation as shown in the slide, and then we will have different values of y. Those can be scaled, or those can be thresholded to generate the desired logic. So here, so we can find the error function value like this for each of the step. So first case is 0.472448. Like that, that will go on to 0.457957 for the steps shown. So we need to calculate the derivative of the error function with respect to the weights and the bias into the output layer neurons. Okay, so step by step, when we do the computation manually, these particular values will come, and for values of 0, 0, 0, 1, 1, 0, 1, 1, values like 0.787754, 0.696717, 0.838124, 0.738777 will come. And then when these are thresholded, and then the thresholding values, if we use log sigmoid, 10 sigmoid, or linear function, depending upon the choice, we will have different values coming, like 0.214990, so on and so forth. So finally, for a set of values, when we go from doing the calculation with 0, 0, 0, 1, 1, 0, and 1, 1, then we will have different values of del 1, values of del 4 at the last stage. So we will find del 4 coming out to be minus 0.04477706. So this will go on, and the values of error function, that E42, E42, E42 can be still shown for 0, 0, 0, 1, 1, 0, 1, 1, 1, 1 combinations. So this how it is calculated. These slides are showing. So if we now make those computations and try to change the value, we see that the new weight from 2 to 4 will be changing to 0.119045. This particular change will take place in the recursion. We are here seeing it done manually, but this will be changing in that recursion that will take place while the training is on. So the weights similarly will continue to change for node 4 for different values, 0, 0, 0, 1, 1, 0, 1, 1, and the new weight will come up to be this minus 0.486441. This will be required to generate the desired response. Similarly, to have change the bias node, we need to have we need to do some calculation. So for 0, 0s and 0, 1, 0, 1 and 1, 0, 1, 1, we need to have a new weight value that is 1.044 that will come up through the calculation as shown there in the slide. So this readjustment shall be the basis of the training, and will make the network suitable for generating a multi-class classification problem. So that same part in a more detailed way. So while we calculate the del, there is a gradient we can see here. So for calculating the gradient, that different layers for different feeds of 0001 and 1011, we see that the weights must change continuously, and then a final value will come that will give the required value. Okay. So this will go on for all the neurons from 1 to 4. So we find that this XOR one is quite a simple and straightforward problem for the neural network to deal with. Neural networks or the ANN is more capable of dealing with more bigger sets of data and dealing with more uh, complex classification problems. We have seen throughout the last 4 or 5 decades that these networks have dealt with all types of real world situation, ranging from the character recognition, ranging from pattern recognition to doing diagnostic uh, classifications. So we need to have we need to have an eye to make the training more reliable. We need to have a training set. We need to have a validation step. We need to have a test set. So when we have this set, these training, validation, and testing can be done separately, and then normally we we should not give a test time result by the use of the training set. So the set that we use for the training part should be separated out. So the test set should be separate. So if we give a result by the use of the training set, then we will see a bias result, means highly means higher success rates may come. Therefore we need to use a separate set for doing the testing part, so the results derived that way will give us the true capability of the system. Further, while we have the training, there should be sufficient variation in the data set through which we can make the training sufficiently robust, because in the real life situations variations come in many forms, in manifold way. Therefore, to have a robust nature of the network developing, we need to have sufficient variations in the data set. Then there are certain cases, like there can be a problem with the convergence. Convergence may stop at some point of time. Uh, while you do work with the multi-layer perceptron or the more generic ANN, you will find that convergence of the gradient stops at some point of time. Now the naive designs can be you can have too much correct weights taken. That can be a situation. So if you have very correct weights taken for the situation, you will have the learning stopping. You can have the gradient convergence stopping at some point. And if you do not have sufficiently close weights or sufficiently distortion free weights, you can also see that the training to be suffering. Then we find sometimes that the training gets stuck at some wrong place. Wrong place means we started with the random weights. Then we had not stopped it at the right time. We had no know-how where to stop. So the training went on, and it stopped at a point that we did not like. So we can have a undesirable classification and performance coming out. So we have no guarantee that we found the best set of weights. So we could get stuck in a local minima situation. That can be a very crucial point. The most discouraging factor of the ANN training shall be the fact that it has the possibility of getting stuck at a local minima problem. So we need to have all the uh, requisite calculations back in the mind and back in the process beforehand, that we get rid of the local minima problem. So here are two situations. If we make a very highly reliable training that we call the overtraining, then we can find that the classification made by the ANN is too good, very much perfect. So in that sort of a case, we will say that generalization will be lost, memorization will set in. So with the training set, you will have very good performance, so very good performance. But with the test set, your performance will be suffering. So therefore, we need to be careful. So we, in that situation, we will find further that the classification will be nearly good, very good, perfect. So you will have very little, say, misclassification. So if we do it with the training set, but if we do it with the training set, with the testing set, then the results will be different. So here is such a situation. So, so how to deal with these situations? We can use a technique like simulated annealing. That is one such way. That means we need to have learning rate variations. We need to have the gradient scaling up, scaling down in a more controlled way, layer by layer. Then we can have a more sophisticated control of the gradient descent process. So if we can do that, we will find that the convergence and learning will be somewhat better. So since we know that the multi-layer perceptron and the ANN is an empirical study, it seems to work out in most cases that we know about. So because it is a non-parametric tool, not much bothered regarding the source of the data, till we have the data, so it can deal with all types of situation, and it has very prominent statistical has the capability to deal with uh, statistical pattern analysis. So that is its strength. So you can have a number of layers, you can have a number of nodes there in the layers to make the training more robust, make the training more divergent, make the training more reliable, and make the learning more stringent. So now, how to do the decision making? You need to have your own way of interpretation, so you can have the results configured as good or bad, do a thresholding in a proper way, and then how many firing output neurons you want to use, that part is dependent on the degree of certainty that you want to have in the process. So where you use it in a thousands of ways, all known forms. You can use for the classification of cancer. You can use it for the classification of network breaches, cyber attacks, pattern competition. You can use it for noise reduction, compression finding, distortions. You can use it for time series compilation, and so on and so forth. Means all known domains. We have seen that the ANN, or the multi-layer perceptron, has found its use. We will find that there will be no end of the ANN. By about 2009-10, before deep neural network came, there was so much of growth in this field that people said that this particular technology has reached saturation. But now we find that with the growth of the deep neural network, the next 50 years will be dictated by the deep neural network technology. There will be no dearth of possibilities, and with big data coming up in a big way, the combination of this neurocomputing and big data will have a very different world of computation and capabilities coming to us, coming to our present day civilization. You can read the first book. You can refer the first book, Neural Network: A Comprehensive Foundation. That is considered to be a Bible. Still, Simon again is living. He lives in Canada. A great man. And this book is very good, very well written. And nowadays, the good thing is that you can make searches in the Google. There are thousands of contents. So, so before I sum up, I would like to request you to raise a few questions. I would be pleased to reply.
Not a technical question, but would you be able to provide us with the presentation
Yes.
slides?
I shall be sharing you this slides also, and recording also. I shall be sharing with the.
Sure. Actually, it's like we have too much other homeworks
Okay.
right now, so I'm not able to like give a lot of time to what you've been teaching. But I'm really interested, and I'll take a look. I'll take a better look when I'm like more
Yes.
focused into this.
Yes. Sure. I shall be sharing it. Sure. Okay.
Thank you, sir.
Thank you. So, somebody would like to raise a question? One question, two question. I shall be pleased to reply. So I think.
Okay, I got another question.
Yes. Please. Yes.
So for my master's thesis, I am working on this, let's say, home automation thing.
Okay.
And I have this. I am not like I'm not. I have not. I haven't begun the. I haven't begun working on it yet. But I have this like I have planned it out properly, and I kind of want to use OpenCV in that,
Okay.
and like for I don't know, to store people's data so that I can like confirm who they are and everything.
Yeah.
Would you suggest me anything else, or OpenCV is like a better option?
Yes. Your for the pattern capture part, this one is good.
Uh-huh. But you see,
OpenCV is good.
the fallouts here are like you can just print a picture and just show it in front of the camera. It will still
Yes.
let you in.
For decision making part, you need to
Mm-hmm.
use some learning tool. So for your case, since you are from the computer science background, therefore
Mm-hmm.
to develop a career from it, you can
Mm-hmm.
use the Google Colab, where
Okay.
there shall be deep learning tools. And in the deep
Mm-hmm.
learning tools, you have many built-in or pre-trained tools which can
Okay.
learn your patterns like the faces, who are the legal faces, who are not the legal faces. So these sort of classifications can be done well, and you can also control it through an app. So something in that line.
Sure, sure.
So if
Uh-huh.
you can have the main gate of a premises controlled by a camera, facial recognition can be linked to it. So the
Mm-hmm.
camera will read the face, that will go to a cloud server. That particular cloud server will be running a Google Colab based deep learning tool or a learning tool. So if
Mm-hmm.
that particular face is classified to be a legal one, the door will be yes, you can come in. And if it is not, that that, that shall say no. So this can be done well, and that can be a very uh, say prominent feature of a smart home that is required. And I would suggest you that you should become familiar with the Google Colab. That's a
Right.
very good platform, very good platform,
Uh-huh.
and free of cost. Lots of things are there, lots of uh, content, lots of codes. There is a community. You will take about 2 weeks to learn. Once you learn, then I think for this sort of work, you will be doing it in thousands of ways, in thousands of new and fresh ways. You will like it finally, and your skill sets
Sure.
will
Thank
go
you
up.
so much, sir.
Uh-huh. Your skill sets will go up. You will feel
Mhm.
proud later on that I did this, and your
And
value will.
sir,
Yes.
mhm, can I have your personal email too?
Why not? Why not? I shall share here. Yes, I will share here.
Just in case I have a few doubts later
Yes,
on.
please. Yes, please, please. So I have
Right.
shared. So
Yes, sir. I got it.
yes, yes, yes.
Anyway, sir, personal question. Do you speak
Yes.
Hindi?
Why not? I
गुवाहाटी
can speak. I can speak.
एक्चुअली गुवाहाटी में मौसम कैसा है सर?
And now अब तो थोड़ा सा ये है 33 डिग्री है, 33 डिग्री सेंटीग्रेड.
हाँ
थोड़ा सा
हाँ
ये दफा मैंने टेम्परेचर कुछ ये है, ज्यादा है. And
हाँ.
now ये टाइम में it's roughly around say 25 डिग्री सेंटीग्रेड. But ये
25
साल
इधर
के
तो
बाद
सर बहुत ठंडी हो गया है. इधर
नहीं
तो
नहीं
5 डिग्री 4 डिग्री.
ओ, यहाँ ये दो मने ये चल रहा है, मने पंखा चल रहा है.
हम्म.
दो
हाँ
पंखा.
सर, इधर पे हम लोग पूरे समर्स पंखा नहीं चलाए.
ओके 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 ओके. ग्रेट 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 ग्रेट.
अच्छा एक्सपीरियंस है. अगर आप कभी आ सकें इधर पे तो बिल्कुल आना. बहुत
यस
अच्छी
यस,
सिटी है,
जरूर
बहुत अच्छा
आएंगे.
जगह है.
I had gone there in 2012.
12, yeah, okay,
हाँ, हाँ.
that's nice.
बहुत बहुत नाइस जगह है, सुंदर जगह है,
हाँ
लोग भी
जी
अच्छा
सर.
है. लोग
हाँ
भी
जी सर,
अच्छा है.
बिल्कुल बिल्कुल. यूनिवर्सिटी में भी अच्छा है. पर्सनली जो लोकल्स हैं वो भी काफी मतलब ठीक है. उनको कोई मतलब नहीं है अपना जो काम
ये
करो.
यस यस. अच्छा.
ओके, थैंक यू सो मच सर.
ओके, थैंक यू, बाय बाय.
बाय बाय.
यस, सचिन, बाय बाय. बाय बाय. थैंक यू.
Bye.